one of Steve's visions was for us as a collaboration to come together and try to extract from this, marvelous, from LSST, this marvelous camera and instrument that they're building, information about dark energy. So the goal of this next hour or so is for us to get together and to try to understand how we're going to do that. We'll start from physics and try to explain some of the ideas that have been put forth to explain how or why the universe is accelerating. And then we'll go end to end, we'll try to understand how we'll be able to test those ideas. Those ideas are going to change. So we as a collaboration have to have the tools to be able to test whatever ideas come up over the next decade or so. So what we're about to walk through is kind of a framework for implementing those ideas into our analyses. So the starting point is the action that describes the whole universe. So that is, we're not going to really use this, so if you're not, if this is Greek to you, don't worry about it. But you integrate over all space. This is the metric. The metric describes the way that coordinate positions are transformed into distances. And then there's something called the Einstein-Hilbert action. So this R is the Ricci scalar and G is Newton's constant. This R is a functional of the gravitational metric. So this encodes gravity. This one term is Einstein's theory of general relativity. And then this couples to the Lagrangian of the standard model of particle physics. So this one equation describes all of physics, right? And and you notice that the matter is coupled to the gravitational effects. You can apply this to any system because it explains all of physics. When you apply it to the universe at large, the large homogeneous universe, you find out that the universe is expanding so that every point is moving away from every other point. And we tend to quantify that with what's called a scale factor, A, so that distances are proportional to this scale factor, which is increasing with time. That's how we're going to quantify it. So this scale factor is embedded in this metric. When you minimize the action, which is what you do in a physical system, you get an equation for this particular system, the universe at large, that is an equation for this scale factor. And the equation looks like this. So this is what's called the Friedmann equation. So this describes the time derivative of the scale factor. It's proportional with a proportionality constant given by Newton's constant to the average energy density in the universe. Is this difficult to see from the back? Is that it? Okay, that's too bad because there's only one blackboard. But then there's, so this is the average energy density, and this is the 2 powers of the scale factor. Actually, it's plus 2 powers. So it's 2 powers of the scale factor. So the thing that rubs you as soon as you see this equation is that imagine we're locked in this room for an hour and the room doubles in size. The density is going to go down, right? The total energy will remain the same. The density will go down by the volume. The volume scales as the length cubed, so the volume will increase as a cubed. So that means this rho bar is going as a to the minus 3. So what you typically expect is there a clock here? There's no clock. What you expect is that the scale factor should increase with time, but that as the universe expands and a gets larger, that rate at which it's decreasing should fall as a to the minus 1/2 power, right? This is minus 3, this is 2, minus 1, square root of that. So what that means is as the universe gets larger, you expect the rate of expansion to decrease. That is, you expect a double dot to be less than 0. You expect deceleration. In fact, what we observe is acceleration. So we're able to observe how distances have evolved with time, and we have observed that the universe is accelerating. Thank you very much. Appreciate that. Okay, so that's the conundrum. And in order to fix it, there are 2 general classes of solutions, 2 possible solutions. The first one is called the right-hand side solution, or dark energy. And that is, this equation is pretty concrete. It comes from the fundamental equation of the universe. So in order to fix this equation, you can imagine adding something to the right-hand side of the universe. That is, what's in here is not the full, is what's encoded in the standard model doesn't have everything. Maybe there's a new thing, we call it dark energy, that has to be added to this thing. The dark energy, though, has to be weird, because the dark energy has to be such that as this room doubles in size, the energy density remains constant. It means it's almost a property of empty space. So it's very, very difficult to come up with physical models with substances that have that property. So what we've relied on is just to parameterize our ignorance in the following form. We parameterize dark energy by saying, or actually any fluid has this property, that the energy, the evolution of the energy with respect to time is equal to its value today at t naught, and then it evolves with time like this. So this is the way it evolves with time. So W here is called the equation of state. For example, if ordinary matter has W equal to 0, and therefore when you do this integral, this just becomes minus log A. So e to the minus 3 log A is a to the minus 3, which is exactly the result we found before, right? That normal matter just gets diluted as a to the minus 3. Dark energy has to be different. It can't dilute. So one of the simplest ways to do it is to just let this whole argument of the exponential be 0, which requires W close to minus 1. And in fact, so another example is W equal minus 1, which is called a cosmological constant lambda. So that's one possibility for dark energy, but there are many possibilities. The key is the substance has to have this equation of state that's much different than ordinary matter. So what we're going to do in the next hour or so is use data to derive constraints on the equation of state of dark energy. Any questions about that? Okay. There's a second possibility. The second possibility is called the left-hand side. And that just means instead of adding stuff to the universe that doesn't exist, we're just making it up, we change the laws. We change the law of gravity so that this Einstein-Hilbert action is not the true action. There are other terms. So you modify gravity. So this left-hand side solution is called modified gravity. And there are many ideas for doing this. Right now, I'd say the most popular one is, you know that gravity is, just like electromagnetism is electromagnetic fields are conveyed by the photon. That's the particle that conveys electromagnetic fields, the coherent state of a photon. Similarly, gravity is kind of, the corresponding particle is the spin 2 particle, the graviton, right? So one of the most prevalent ideas today is to give the graviton a mass. So on the one hand, you think that kind of makes sense because, especially those of you coming from particle physics, know that if you give a particle a mass, that means the force that it mediates has a finite range. So if you give, for example, the pion a mass, it has the range only on the order of the nucleus. Similarly, if you give the graviton a mass, it only has a finite range. So you give it a mass roughly the size of the universe today, inverse size of the universe today, then the force of gravity falls off after that. And that would explain why the universe is accelerating, because gravity becomes less important. So that is something that that's possible. And either of these things, I mean, both of these names are a joke. So you can now laugh at the joke, because it obviously doesn't matter whether you put something on the left-hand side or the right-hand side, you can get the same equation, right? But so as a result, what we find is both theories, both modifications, dark energy and modified gravity, can get any observed distance relationship, A of t. So for example, supernova and baryon acoustic oscillations and other probes have measured these distances as a function of time. You can explain those with either dark energy or with modified gravity. So the question becomes, how are we going to distinguish the two? how are we going to distinguish dark energy from modified gravity? And the answer lies in the perturbations. That is, you take this exact same Lagrangian and you apply it not to the smooth universe, but account for the fact the universe is not completely smooth. We exist, for example, right? So therefore, the density at any given place in space and time is equal to this average density times 1 plus some overdensity or underdensity that depends on space and time. Right? And so what's going to happen is, there are more people on this side of the room than on this side of the room. So over the course of 13 billion years, all of these people are going to eventually accrete onto this side of the room because of gravity. And so what you can imagine doing is plotting, so as a function of time, say, as a function of time, say, you can plot the evolution of the density at a given spot in time. And if it starts, down here lower, eventually it's going to grow with time. And in fact, I'm trying to draw that. So the effect of dark energy is a relatively recent phenomena. So I bungled this plot, but the basic idea is the growth is kind of impeded a little bit when dark energy when the universe starts to accelerate, because at that point it becomes more difficult for stuff to cluster, because a lot of the density in the universe is not clustering. So this is supposed to, let me just erase it. This growth function, it's called, kind of turns over at late times because of the acceleration. So this is in a model with general relativity plus dark energy. In a model with modified gravity, and let's take the example of the graviton mass as an example. It's true that the force falls off at very large distances, but you remember that if you have a massless, say, photon, it only has 2 degrees of freedom, whereas a massive boson has 3. Similarly, with the graviton, if you give it mass, it has extra degrees of freedom. And in fact, generically, almost all modified gravity models introduce extra degrees of freedom. And what that means is they introduce extra forces. So in fact, in most modified gravity models, the growth is faster. It's not a theorem, but you can kind of see why it's true in general. So what we can hope to do, therefore, is distinguish these two broad classes of ideas, changing the basic laws, modified gravity, or introducing new stuff, dark energy, by looking at the growth of perturbations. So we're coming up on the first exercise for you. And it's clear that no theory is going to predict, there should be an overdensity over there, but not over there, right? So we're going to have to make our money using statistics. And the first statistic you might think of using, the average value of delta, is not very useful because by definition, the average value averaged over space is just 0, right? So that doesn't help very much. So in fact, we're going to make our money calculating the fluctuations, the RMS fluctuations. So start taking out a pencil and paper. I'm going to ask you to compute this, but first let me give you a little bit of information. It's useful to Fourier transform the density like this. This is going to be our Fourier convention. So these Fourier modes. These Fourier modes are independent typically of one another. So if I would plot a histogram of the Fourier modes, then it would look something like this. And the width of this thing, or the variance of this thing, is called the power spectrum. So the width of this histogram is 1/2 of the variance, or P of k. And because of symmetries, the histogram depends only on the magnitude of k, not on the direction. So essentially what you have is a lot of independent modes for a given wavelength or wave number. And each one of those is drawn from the same distribution, but they're all independent. So I'm going to ask you now to calculate this, but I'm going to encode in equations what I just said. And that is when you take the expectation value of 2 Fourier modes, then you get the power spectrum. You get a delta function that the Fourier modes are independent of one another. unless it's the same Fourier mode. And then there's just some normalization factor. Okay, so start. I'll give you a couple minutes to try to compute the variance of this thing, the variance of the fluctuations in terms of the power spectrum. Yeah. This is just a picture that shows you, this is the histogram. This is the square root of p. Because the variance is p, so the RMS is the square root of the variance. But you don't have to look at this. You could just use this formula. So take the square of this thing, write it in terms of its Fourier transforms, and then use this fact to compute the variance. So in terms of P of k, yeah. Yeah, it has nothing to do with rho. Just plug in, forget about this equation. Just use this expression and this expression for the power spectrum. This is not a Kronecker delta. So there's a lot of deltas floating around. This is the overdensity as defined here. This is the Fourier transform of that overdensity, which depends on wave number k, which is not x. This is the Fourier transform. This is the power spectrum. This is a Dirac delta function, a three-dimensional Dirac delta function that requires k and k prime to sum to 0. So that will be quite useful to you, because Dirac delta functions are very useful when doing integrals. Okay, so I'm going to finish up if you like, but let me just walk you through it. So what we should have is this delta squared. We wrote delta twice. So all I've done here is written down the Fourier transform twice and collected terms. We know that this thing gives us this delta function. Times the power spectrum. Using this delta function to do the k prime integral, the 2 pi cubes go away, the k prime goes away. K plus k prime is just 0. So what you're left with is an integral over all wave numbers of the power spectrum. And I argued that the power spectrum itself depends only on the wave number, the magnitude of the wave number. So the angular integral just gives a 4 pi. So what you're left with is the integral dk over k times k cubed p of k, which you can check is dimensionless, divided by 2 pi squared. So essentially what this is this, it says the fluctuations in space depend, you sum over all scales. There's a logarithmic sum over all scales. And the contribution comes from this dimensionless quantity of the power spectrum times k cubed. So what that means is, if you wanted to, a useful thing to do is to plot this. And as you plot this, what you'll find is it's increasing as k gets larger. Remember, large k is what's it called to x? The complementary variable. What is it called? Conjugate variable to x, which means it has the dimensions of 1 over length, 1 over wavelength. So as you get to large k, that corresponds to small wavelengths, small scales. And that means as you go into small scales, what you find is that this dimensionless quantity is getting larger, and the value of it is important. It's a dimensionless number. On large scales, it's less than 1, which means the fluctuations are small on large scales. And as you go to small scales, the fluctuations become larger than 1. And that's reflected in the fact that we are here. And the density in this room is 30 orders of magnitude larger than it is an average place in the universe. So on very small scales, this thing is very much larger than 1. On large scales, it's smaller than 1. Any questions about that? Okay, so an exercise, how many people were able to download Cosmosis before the lecture thing? Sort of. Okay, so about half. I suggest if you start gathering around people who have done it in a minute. But one thing you might do is, has anyone run demo 1? Yeah. Okay, so in demo 1, you should be able to generate the power spectrum, see what the power spectrum looks like. So if you type post-process, post-process demos, demo 1. You might have already done this. Is that part of the demo, Elise?
This is the thing that I told you about.
For demo 1?
This is the thing that I told you about, that it wouldn't run unless you...
I thought you said demo 10. Okay.
No, well, that's a separate problem. But
Okay.
Nobody can run any of them unless they...
Okay, so how many people were successfully able to run this post-process? Okay. So, and how many people were not able to successfully run this? Okay. So you're able to run the demo but not the post-process? Okay. So the demo, if you look at the demo, where is the text file, Elise? It's in demo 1. Where's the power spectrum file? So if you... Okay. What about before post-process? What about before post-process? In which folder is it in? Okay. Okay. So if you successfully ran this command post-process demos demo 1, then you should have a plot in plots, which is essentially the power spectrum. It doesn't have the k-cube, it has the power spectrum. So I would look at that. If you did not successfully run post-process, then there's a file in the directory output underscore demo 1. Is that right, Elise? Then, and there's a subdirectory under that called power spectrum, and that has a text file which contains the power spectrum. Or maybe it might be called matter power spectrum. Matter. So that has a text file which contains the power spectrum. So you can play with that at your leisure to show that this happens at a k value of about 0.15, and this is in units of inverse megaparsec. And for those of you who are not astronomers, a megaparsec is an awful unit because we were handed by God this great unit of light years, which everyone understands in second grade up, and we screwed it up and turned it into megaparsec, which no one remembers. But anyway, this is about 3 million light years. So that's in the process. Okay, so let's move. Yeah.
Is this the plot we're supposed to be looking at, the matter power spectrum plot?
Exactly. Yeah.
You said at 0.15 it should give me 1.
When you multiply that by k cubed, so that y-axis in that plot has dimensions. When you multiply by k cubed, you'll see that it monotonically increases, and it goes above 1, which is you can actually, by eye, figure it out. When it goes above 1, you'll see it's about 0.15. Okay, so that's good. We can see that what we'd like to do is measure this power spectrum of the matter in order to distinguish modified gravity from dark energy. Now let's talk a little bit about one way to do that, and that's gravitational lensing. So we're going to take 3 or 4 passes by this. First, let's point out that the way that gravitational lensing works, at least one of the ways within LSST, is the following. Imagine you have, you're sitting in the back there, and there's a foreground bunch of stuff. And then in the background, there's a circular galaxy. Okay? So you're over here, this thing is over here, and this background galaxy is a circular in the back. Got it? That's the scenario. Now what's going to happen? So the light ray from this thing, as it passes by this foreground mass, is going to get deflected. Right? So we're going to see this guy as if it's coming from a distance further away. Does that make sense? In other words, this light ray is going to be deflected so that it will appear to be coming from up there, right? Because it's coming like this, and we trace it back, we're going to see it like that, right? The light ray from this galaxy, from this part of the galaxy, is not going to be deflected nearly as much because it's not passing as close to this foreground mass, right? So let's call that no deflection. And similarly, everything in between will be deflected an intermediate amount. So what's going to happen, this circular galaxy is going to appear to us to be elliptical. That's the effect we're looking for. Does that make sense? So in order to understand, in order to glean information about the foreground mass distribution in the universe, we want to measure galaxy shapes. That's qualitatively what we're after. And so if you start with this action, and you can derive an equation called the geodesic equation for how light propagates through the universe. that accounts for this deflection of light. And when you apply it to this situation, so imagine you have we're over here, and there's some source a distance ds away, and the source looks something like this, and it's an angle theta away from us. And the question is, how does light propagate as it traverses this distance, given the fact that there's inhomogeneous matter in between us and the source? Do people see the geometry here? Okay, and there's an equation for it, the geodesic equation, which follows directly from this action. Let me write down what the geodesic equation is. The second derivative of d theta I, of d theta. So theta is this angle. D is the distance along the line of sight. So this thing, in astronomy, you never have to worry about sines or tangents because it's small angle. So theta, the perpendicular distance, is always equal to theta times the distance to you're at. So that's a great thing about astronomy. You don't have to know trigonometry at all. Okay, so then anyway, the geodesic equation reduces to this. It's a very simple equation. It's the gradient of the gravitational potential. So we're going to solve this equation in a second, but right away you can see something magical. And that is, if we can observe this effect, then we can learn about the intervening gravitational potential. And remember, by Poisson's law, the gradient of the potential is related to this overdensity. And this overdensity is the power spectrum that encodes the information about the growth. So if we want to learn to distinguish between dark energy and modified gravity, one way to do it is to measure how this thing is growing, or to measure how the gravitational potential is changing with time. So we can do that by using lensing, because lensing is directly, the deflection is directly governed by this gravitational potential. Okay, does that make sense? The solution to this equation is straightforward. It turns out that the deflection angle, which is if this is the true angle, if this is the true position, then the deflection angle is just the amount by which the light is deflected, but the mismatch between the true position and the observed position. So that deflection angle, it turns out, is equal to, you integrate up to the line of sight. Maybe there's a factor of 2 here. You integrate along the whole distance up to the line of sight, and then you take this gradient of the gravitational potential, and then you have 1 minus d over ds. That's the answer. If you just integrate this twice, you get this answer. And that does have the right dimensions. Okay, so that's the equation that you need that relates the deflection angle to the gravitational potential. The deflection angle, though, is not what we want. Because if this whole galaxy were deflected together, we wouldn't know. We'd just see a circular galaxy again, just in a different position, but we wouldn't know the initial position, so it doesn't help us at all. So what we want is how that deflection angle is changing with angle. Right? We want the fact that the bottom of this galaxy is deflected more than the top. So we really want the change of this deflection angle with angle. That's what we want. So what's observable in terms of the shape, is the derivative of this deflection angle, which has 2 components, x and y components, with respect to angle, which also has 2 components on the sky. So that's what we want. And that thing is just equal to, there's probably a 2 again, an integral over distances. And then there's another power of distance, 1 minus d over ds. And then it's the second derivative of the gravitational potential. So that's the bottom line. You measure this thing in terms of shapes of galaxies, and you infer this thing in terms of, which is what you want, which is going to give us information about the gravitational potential. Does that make sense? Yeah.
So, 2 questions in the galaxy to start with.
Okay, good. So
stack them, is that why
good question, but both good questions. The first question, people, including me, have spent a lot of time looking at second-order perturbation theory. It turns out to be small. Perturbation theory just works. But the potentials are quite small. They're of order 10 to the minus 5. Remember that number. So the perturbation theory works pretty well. The second question is very important because obviously not all galaxies would appear circular without the distortion. But as you say, on average, they would. So when you average many different galaxies together, the average ellipticity will be 0. So essentially what that corresponds to is noise. So what we're looking for a signal which is the ellipticity by a given mass distribution, and that's in the presence of noise. So we're going to try to extract the signal from the noise.
So when we go to the strong lensing regime, true just to first order here.
In strong lensing, this is still the correct equation. This is still the correct equation. In strong lensing, the thing that nothing breaks down in these equations. These equations completely describe strong lensing as well. Nothing breaks down. Okay. This is called the distortion matrix. So in strong lensing, there are places where the determinant of this 2 by 2 matrix vanishes. And that corresponds to very weird things, because what does that mean? That means as you change this thing by a lot, this thing just changes by a little bit. Or vice versa, if you change this thing by a little bit, the images change by a lot. So but this matrix, this equation describes everything in lensing, strong and weak lensing. Okay, so this is the observable. Now I'd like to ask you a question. This is your second exercise. And that is, okay, on average, this deflection angle and variation are going to obviously vanish over the whole universe because the gravitational potential is fluctuating, up and down, up and down, up and down. But again, what we're going to make our money off is the variance. So what is the variance of this thing? Let's call this whole thing the distortion tensor, say. So what is the variance, or the RMS, the variance of forget about the indices, they're not important. What is the variance of this thing? And in order to do that, let me just make one generalization of the previous thing. This is a 2-dimensional quantity, not a 3-dimensional quantity. So therefore, the variance we know is going to be very strongly related to what we had in the last one. We had dk over k. We had L cubed p of k. Here we'll have L squared CL, where CL is exactly the same thing. If you Fourier transform, and CL is just the power spectrum in 2 dimension. So there's a histogram for each mode. It's drawn with the width CL. And the power on each this is angular scales, is going to be equal to this dimensionless combination. Okay? A little complicated, a little quicker. I should have done this earlier, but that's the basic idea. The RMS of these fluctuations in the shapes, which are going to be the signal we're looking for. We're going to be looking for, essentially, to measure this spectrum. That's going to give us information about the gravitational potential. So the question is, what is the expected amplitude of this spectrum? Okay? So that's your next exercise. And I would start from this equation. And right? So this has 2 powers of distance in here. You know what distances are in cosmology, roughly speaking. And then it has the gravitational potential. I just told you what a typical value for that is. And then it has the scales on which the gravitational potential is changing. So what is a typical value for this? And this, you can feel free to talk among yourselves for. So someone asked a good question. What's your name again? Siddharth. Siddharth asked a good question. What's L? So it's exactly the same thing. We Fourier transformed the field. Before it was the delta field. Here it's this distortion tensor, which is going to be a measurement of shapes. We Fourier transform it in terms of angles, because it's angles on the sky. So this is the Fourier transform. Again, the L plays the role of k. Here it has dimensions of 1 over angle, or radian, 1 over radian. So d2L, e to the I L theta, psi L, in the Fourier transform. So just like in the k thing, large L is going to correspond to structure on small scales, right? And small L corresponds to large scales. Good question. So that's it. But it's the same exact thing that the psi twiddle of L prime, that's going to be equal to CL. So CL plays the role of the 2-dimensional power spectrum. So I'm not asking you to do this the same calculation you did before. I'm asking you to do an estimate of what you think the RMS is of this, this is a matrix really, but just this thing, let's just call it a thing. What is the RMS of this thing? It's going to fluctuate with mean 0. We'll have an RMS. What is the order of magnitude of that RMS? An estimate of this effect. The gravitational potential I told you is, so L squared CL over 2 pi. This is going to be the variance in this thing. So the variance is going to be the variance of phi. I told you phi was roughly 10 to the minus 5, so that's 10 to the minus 10. And then you have cosmological distances. There's 2 powers of those. Typical cosmological distances are about 1 gigaparsec. And that comes in squared. When we take the square of this thing to get the variance, we'll get it to the 4th power. And then what I didn't tell you is the scale on which the potential is changing. So you had to guess that. And a good guess would be about 10 megaparsecs. And that again comes in as the 4th power. So our first guess for the amplitude of this spectrum, this is 1,000 over 10, which is 100 to the 4th, 10 to the 8th. So it's about 10 to the minus 2. It turns out that's too high. And the reason it's too high is very interesting. If you think about, we're looking over here and we're looking out to some distant galaxy. If you think about Fourier modes that look like this, with large kz, are not going to contribute, because you get plus, minus, they'll go away. So you only have a fraction of the Fourier modes, those with very small kz. So only modes with kz smaller than 1 over these cosmological distances, only those contribute. So now think in Fourier space for a given, I guess this is L space, sorry. Well, no, this is not. So think in Fourier space for a given, this is actually in 3D space. In Fourier modes, there's a shell of radius k, but not all those modes contribute. Only the ones with small kz and a ring around the origin contribute. So only a fraction of those modes contribute. So you can do the geometry of that sphere, and that reduces this by a further factor of this lambda over d, 10 megaparsec over 1 gigaparsec, and squared. So the expected amplitude, I didn't explain that well, but I'm doing it quickly. The expected amplitude then is about 10 to the minus 4. So look at demo 6 if you did that. You actually calculated the shear. And that's a good time if you could group yourselves among people who were able to successfully get cosmosis installed. That would be useful. That's the thing, that's the change. And so that tells you we're going to sample a grid. We're only going to sample through one parameter though, W. So your exercise is to change the file. In this case, the file is dssvvalues.ini. And you want to change the file so you only sample through one parameter. You only allow one parameter to vary. So your exercise is to change this file, and first the other file the way I showed you, change this file to allow W to vary, and nothing else, unless you want to wait a long time. Yeah. So in this, the sampler tells you how you're sampling the parameter space. The way that file was set up initially in Cosmosis, it was, I think, Fisher or something like that. So I'm asking you to change it to a simple one, grid. It just evaluates it on a grid of parameters. And you just have to define what grid is. And one of the parameters that's needed is how many values of the parameter it samples. So that's this parameter, n sample underscore dimension, and set it equal to 20. Or 10, whatever. And the other file is the values file, that's right. So people should, this is a really collaborative exercise, especially if you don't have Cosmosis installed.